All right. So hello, everyone. This is all the participants we have for now. Let's hope some more trickle in as we get further into this workshop. But yeah, I'll hand it off to Mr. Wolfram. Um,
Okay, well, we got so few people. Okay, can you all switch your cameras on, please? Then we can have a good chat. Anybody there? We have a dog. Oh, we have a person. Hello. Pleased to meet you. Just a second. And let's see, anybody else? I want to see that dog. Oh, okay. Give me 1 minute, you say. All right. So are you in Lexington, or are you somewhere on the other side of the world?
I'm in Texas.
Okay. So I figured that, all right. So how about our organizer person? What's the name of the person who was the original person who invited me?
Hi. Yep, me. I am Nate Harris. Yeah, I live in Lexington. I am a part of the team here at LexHack. And
Okay,
yeah,
great. What stage of high school are you at?
I'm currently a sophomore in high school.
Okay. All right. Well, let's see. So, I was kind of expecting a different crowd here, but all right. Let me see. Well, we can if you want to. I'm not really the best person to give you the what to do in your hackathon project speech, but we have a good page, which let's see, I can put this page in the chat. And this might be a good place to start if you'd like to understand. Let's see, a really cool thing to start with is this hackathon project generator, where you can, okay, it does pretty well, actually. If you just press generate another idea, it will generate suggested things that you can do with our technology stack that are kind of hackathon-sized things. And I think we've had let's see, there's a good collection of people who've done all kinds of interesting things over the years with our technology. But I'm not sure. Maybe I should. Hold on 1 second here. Well, okay. Who here has used Wolfram Alpha? Let's start with that. Yes, yes, a few yeses. Okay, good. To do math homework or to do other kinds of things? Other kinds of things. Math, something else. Well, okay. So look, we can talk about a whole variety of things. And with this smaller group, really, it's best to have a chat. I don't think it's the right thing for me to sort of give a speech here. I mean, we can let's see, the person who originally invited me was a Sahil. Is Sahil here?
I don't think Sahil's here. He's also another one of our staff, but I don't think he could make it to this meeting, unfortunately. So I will be moderating.
I'm not sure this meeting makes sense. If you guys switch on your cameras, or we're kind of going to give up here, because I have a million things to do today, and I would be really happy to do this in person. I live in Concord, Massachusetts, which is, you know, 1 town over from Lexington. And next year, when you've decided you're no longer afraid of the virus, I'd be happy to come over. In fact, I'd be happy. Even this year, I was offering to come over to Lexington and get ice cream for whoever wants it. But are any of you actually in the Lexington area, or are you all kind of remote somewhere completely different in the world?
I'm in Lexington.
Okay,
I am
good.
too.
At least two. Okay, good. Anybody else? Or are you
I
guys?
am also in Lexington.
Okay, all right, fine.
I'm in the Newton area.
Okay, that counts. That's not that there's anything wrong with being in Texas. It's just that it's a different kind of thing. Well, so okay. Well, let's see. We could talk about technology. We could talk about science. We can talk about some other kinds of things. Maybe. All right. Let me try and I can show you. Okay. You can. This is a Wolfram notebook. You kind of type what you want to compute and you get the answer. And you can do this in the cloud as well. So you could follow along if you want to. And you should have, if you go to wolframcloud.com, you could do the exact same things that I'm doing on the desktop version. But maybe let me just show it in the desktop version, and then I can upload the notebook that I make, and you can play with it if you'd like to. So let's so how do we get started? Well, let's say we want to make a let's just say we want to make a list of 20 numbers. So the basic way that you make things happen in our language is there's the name of a function, and then there are its arguments. And the thing that I've been building for the last, I don't know, 40 years or so, let me just save this away, is to have a language that knows about all kinds of things. So for example, we can, let's say, let's capture here, let's do this. Let's capture an image here. I just pasted that image in. And let's try saying, let's just do some computation. Just like we have the function range, which takes an integer and gives us a list of integers, we can have a function edge detect that will go and take that image and detect edges in that image. Maybe we can have a fancier function. Let's see whether this will work. Let's use the function facial features. Let's see what it figures out. This is a function that's using fancy machine learning to try and tell us things about the faces in this image. So let's see what it can do. It might take a little while to load in the neural net that it needs to do this computation. There we go. Okay, it thinks you're a lot older than you really are, I suspect. Such is the way of machine learning. You don't always get the results you think you're going to get. But what it did successfully do is find faces. Okay, it did a pathetic job on figuring out. Okay, it also tried to figure out emotion, but this is let's do something here. Let us take a little screen capture of some of the background from one of you, and let's take that, and let's say we say image identify. Let's see if we can figure out what that is, and I'll see what our image identification system thinks that is. It's often kind of fun what it produces. Okay. Oh, it thinks that's the planet Uranus. Okay, that's amusing. So you can say all. Let's have it give us the top 10 things that that might be. Okay. Boy, it's kind of amusing. It's kind of almost an art criticism type thing of what might that thing be. If you asked a human, they'd probably be confused as well. A Pac-Man. Okay, interesting. Okay, but so let's go back to let's try doing some other kinds of things. So, for example, one of the points of our language is to be able to represent sort of things in the world computationally. And kind of the point of traditional programming languages is tell a computer what to do step by step. The point of our language is be able to express things about the world in computational form. So for instance, we might say, let's get a list of words. That's a list of words in English. And we could say, for example, let's take, so now we have a function string take that takes characters from a string. So that will now take the first letter from every word here. And there are about 40,000 words in that list. And then, for example, we might say, make a word cloud of this for showing us which are the most common letters in English. Okay, so let's say we want to do that for several languages. We could say, for example, make us a table where there is, here we say language is lang, for example. And then we say here, let's make in that table, let's say lang is, and then let's say, I don't know, let's say English, French, German, Russian, let's say. And let's see what happens here. So now what we're telling it to do is make that same word cloud, but let's ask it to do it for all of these 4 languages. It might take it a little while to, okay, there we go. So that's now showing us the comparison. And we should have labeled the language. We could easily have done that. We could have just told it, let's do it just for fun. Let's say we say, make this be labeled with the language here. And now might have to go through much of that computation again, but some of it we'll already know how to do because it loaded in the data. Okay, there we go. So that's now showing us the sort of word clouds of the relative frequency of letters in different languages. So we can do, we can do all kinds of things. What's a field that you guys are interested in? Some let's try doing something. Let's try doing something in geography. So let's say we say let's say US state capitals. So that's using natural language. That's using the same technology we have in Wolfram Alpha to understand that query. And it turns it into this representation in our computational language that says this represents all states, that represents capital city. There we have the results from all those capital cities. And now if we wanted to, we could say geolist plot, and that will show us a map of all those various capitals of the locations of those capital cities in the US there. And so, for example, let's say, I don't know, let's pick Lexington, Massachusetts, just as a Lexington, Mass. Okay, so this now is an entity. So normally in a typical programming language, it doesn't know anything about what Lexington, Massachusetts is. The point of our computational language is to know about things like that in the world. So we can say, what does the machine actually interpret that as? It says it's the entity that's a city, Lexington, Massachusetts, United States. So that's its representation of the city of Lexington. So we could say, for example, what's the population of the city of Lexington, and it should know that. And if we say, for example, we could say something like, give us that across a range of dates. So now it's going to give us a time series here, and we can say make a plot, and this should show us, okay, it doesn't have very many data points. It only has 3 data points here of the population of, oh, it said only 3 data points, the population of Lexington as a function of time, going up slightly. Maybe some of you contribute to the 2020 census by being a data point there. Let's say, okay, let's do this. Let's make a geographics of a geodisk. Let's say we're going to pick Lexington here. That's the object that we're dealing with here. A geodisk represents a region of a certain size. So let's say we say 10 miles around Lexington, and let's just do this. So this now, okay, it'll take a little while to get ready here. And then it should show us a map of 10 miles around Lexington. Let's see what it thinks. If we let's go down to let's say instead of that, let's say 200 feet. So that will now be something around wherever it thinks the center of Lexington is. It'll show us, okay, there it is. All right, that's where it thinks the center of Lexington is, and that's what it's giving us. Actually, what we could do here is instead of saying geographics, we could say geoimage, and this should give us a satellite image of that same location. Let's see what happens here. Okay, oops, I have to say continue here. Okay, so there's a satellite image, and now, for example, we could take that satellite image and we could start doing image processing on it. So let's say we did edge detection, the thing I was doing earlier. So that will tell us, okay, it doesn't really do a very good job of showing us where the streets are. We'd have to be a little bit more clever to figure out where the streets are. But for example, we might let's take that image and let's find let's make a chromaticity plot. So that's going to show us the distribution of colors in that image. So it's going to show us where, okay, so that's showing us, this is the distribution of what color values show up in that image. And we can see the dominant thing. Let's see, okay, you're making various comments in chat. Let me look at the chat and then maybe I can respond to some of the things you're saying. So you're asking other kinds of things. Okay, Ethan says, math homework, math. Okay, well, we can look at some math. Can our language be used to calculate more advanced machine learning? Yes, our system is used for lots of sort of leading edge machine learning research, and you can do all kinds of machine learning with it. Let's see. You're asking, Anish is asking, is the scale for the geographics view dependent on machine learning or hard coded? It's a good question. So if we, I think if we just ask for, in Wolfram Alpha, for example, we actually have algorithms that if you ask for a location, we'll try and figure out what a reasonable map to show in that location is. So if it's in the middle of the Pacific Ocean, we can try that. Let's just go to Wolfram Alpha here. Where did I put my web browser? Where did I put my web browser? Oh, there it is. Okay, let's go to Wolfram Alpha, and let's say latitude 34, longitude 67. Let's see if it understands that. I don't know if it will, but let's see. Okay, there we go. Okay, that wasn't very exciting. That decided to make a local map 20 miles across somewhere in Afghanistan. So I would say that was a lose. It didn't manage to do a good job of figuring out what the scale should be there. Maybe we could try and write some code to do that. Let's see if we can do that. So let's say we let's try writing a piece of code that will get, okay, so let's imagine we have geographics and we say a particular location there, and we say, well, let's think how we would do this. So we're going to pick a location. Let's pick geoposition. Pick your favorite geoposition. Let's say geoposition 5070. I have no idea where that is. Okay, so now we say geo range, and we could say something like 10 miles. And now, now let's say what's, okay, so that was totally boring, 10 miles across. So let's say we make something which goes, let's do this. Let's make this be not 10 miles across, but let's say we go, let's say we have quantity, and let's say we say, let's say 10 to the power n. Let's not say 10, let's say 2 to the power n miles across. And let's then say, we're going to make this a table of those with n goes up to 5, let's say. Okay, so what this is going to do is it's going to make exponentially larger regions around that point. Okay, still pretty boring, right? Those are pretty boring. Let's go ahead and do this for, I don't know, 10 of those. Okay, so now we're going to make we're going to make maps around the point latitude 50, longitude 70. We're going to make a whole bunch of those maps. Let's see what it does. So okay, so now, all right, so now things are getting more exciting here. Okay, this is somewhere in Kazakhstan. Okay, so at this point we might say that's probably a big enough scale for this. Maybe we can just go. We could maybe go and let's go even further. Let's go here to let's say level 14 out here, and hopefully it'll do this faster this time because it's we got too big. The 16,000 miles is too big. Why is it too big? Come now. What's the diameter of the Earth? That's too big. You can't. Yes, please. You have your hand up, Nate.
Yeah, I think that would be too big. It would go around the Earth.
Yeah,
You
yeah,
can't
right,
do that.
right. Yes, yes. It's asking to zoom out so we'd see more than the Earth. Okay, so here we go. Oh, look at that. Now it's okay. In that case, what it did was it just reverted down to something, but it had got up to a whole world view here. So okay, so let's say we want to figure out which of these views is a reasonable view to give. How might we do that? Well, what could we think about doing? We could think about trying to figure out, for example, there is a quantity called, I think, let's see whether this works. Let's see. I wonder whether this will work. I'm curious whether this works. I don't know if this will work. No, it doesn't work. Okay, let's try and figure out something which gives us a sense of whether that picture has anything interesting in it. So for example, we could say of this picture, one thing we could do, it's a real hack, but we could say something like, here's a real hack. So we could say, let's imagine that we are exporting that picture as a GIF, okay? And that will make a big, a GIF is the standard way that graphics are rendered on the web. And what GIFs do is they compress images. So if there's a big area that isn't very interesting, it'll compress it and represent that with less data. So here we could just say, make a string that is that, figure out the length of the string corresponding to the GIF that is that image. What an incredible hack. All right, we can take this output, that's line 27, and we could say, let's take this and let's take that. We're going to use slightly fancy, well, no, we can do it with table actually. Let's say we've got an image here and we'll just make a table of these with the image being the things on line 27. Okay, so now it's going to work out, oops, I meant to say image here. So now what it's going to do is it's going to work out the compressed size of each of those pictures. So that's going to give us some idea. So let's say, let's make a plot here. Let's say list plot of that. So that's going to show us, okay, so that's kind of interesting. So that says, as we zoom out, the picture has more information, more data in it, more incompressible data in it. When we get to very, very big sizes, we're back down to something where there's not a lot of detail in it. So this is showing us probably the picture. So probably it's this picture here that has as much detail as the maximum amount of detail. So if we were trying to make some kind of heuristic, some machine learning thing that would figure out how big a zoom to make, we could imagine just computing how much information content there is using a technique like this in these pictures. Another thing, let's see. So we're talking about machine learning. Let's go back. We had back here. I had told it to identify that image. Okay, so one question is, how does that work inside? And we can take a look at that. So instead of saying, so we can say a net model, this will show us the actual sort of low-level machine learning code. So let's see, what do we want to have? Wolfram image identify net. So this is the actual neural net. And honestly, humans don't really find this very interesting. I mean, this is what happens when you're sort of deep inside the machine. This is what it learnt from lots of from looking at lots of images, and we could see, for example, here, if we use this thing, if we use this net model, and we say let's have it try and identify that image. Okay, it says it's Uranus. Let's say we say don't use the whole neural net, just use the first 10 layers of the neural net. First, let's say 5 layers of the neural net. Let's see what it figured out after 5 layers of the neural net. Okay, we have to make it actually show those as images. Okay, so what it's done is the neural net has figured out to process this image in a whole variety of ways. And in the end, it's going to say, oh, images that look like this, we're going to classify those as being the planet Uranus as opposed to something else. Okay, so now let's take a look. If we wanted to train a neural net, let's say, what's a good example? Let's just take a very classic example. We can take this. So this is a collection of training data that is, if it loads itself in here, that shows handwritten digits and what the actual digit is. Okay, so let's take a random sample of 50 of those. Okay, and let's okay, there they are. And now let's say let's just take the digits from there. So let's just say first of that. So we're just going to get the handwritten digits. Okay, so now one thing we can do is we can say make a feature space plot of that. And what that will do is it will try and arrange those numbers in such a way that it groups numbers that look similar to the machine together. So for example, the zeros all ended up together, the ones ended up together, the 8s ended up together, the 9s ended up together. And so what one does in typical machine learning setups is one uses the fact that one can group things that are similar together, and one can kind of learn what gets grouped together by looking at the original data. So for example, let's say we do the following. Let's take the original data here, and let's take a random sample of, let's make it a little bit easier for the thing. Let's take a random sample of, let's say 400 of those. And then let's tell it to classify. So that will be a bunch of handwritten digits and the actual digit that we're using. Let's say classify that. And so now it will be trying to train itself. It will be trying to learn the association between what a handwritten digit looks like and what what the actual value is. So let's try it. Let's say we got a 7 there. And let's say we take, that's on line 41, it's got that result. Let's feed it that 7. Okay, great, it says it's a 7. That was clever of it. So it learnt that just from seeing 400 examples, and we can probably confuse it. Let's say we take that 7 and we blur out the 7. So let's say we make, let's make a table here in which we take the blur of the 7 with radius r, and let's blur that from radius up to, let's say, up to 10. Okay, so that's getting blurrier and blurrier. So the question is, how far will it succeed in telling us that's a 7, and when will it just give up and start saying something silly? Okay, so let's try that. Okay, so for the first few, it's like, okay, that's a 7. By the time it was this fuzzed out, it doesn't really have a clue, and it says it's an 8 instead. So that's kind of that's showing us sort of the boundary of what we're able to do, what this thing was able to learn. But so that gives some idea of what kind of how you would train a neural net here. And the typical kind of form of training is you've got a set of examples where you say, and this is a that. So for example, let's do another example. Let's do a web image search for cats. For cats, no, let's do something more interesting. Let's do tigers. And see what we get if we have, if we do, this should get us a bunch of images. Okay, there are a bunch of fine images of tigers, and let's do a web image search for an elephant. So that will get us a bunch of images of elephants. And then what we're going to do is we're going to try and train a machine learning classifier to tell tigers from elephants. Okay, so we've got our tigers on line 45, our elephants on line 46. Okay, so let's do this. We're going to have to do some slightly fancy footwork here to line 45. goes to tiger. And then let's join that with line 46. Going to elephant. And then, okay, so then we have a training set of tigers and elephants, okay? So now what we do is we say classify. Classify is a sort of super function that we have that will just try and do the most sensible machine learning thing it can. And actually what I should have done here is say, let's call this a classifier. Classifier function is equal to, that was on line 47 there, classifier function, and let's get it to, okay, there we go. So now if I feed that particular image to the classifier function, if it isn't completely silly, it will say it's an elephant, okay? Because it learnt that from that training data. Okay, let's try seeing if we just ask Wolfram language for a picture of an elephant. Let's see what, okay, the African bush elephant image. There's an African bush elephant image. Let's see what happens if we feed that image to our tiger elephant classifier. Okay, it said it's an elephant. So even though it had never seen that particular picture before, it was able to tell the difference. Now, if we were to feed it, let's feed it a picture, let's say picture of a lion. So now it's going to have to decide, it's got a picture of a lion here. Let's look at this picture of a lion. It's got to decide if we feed it that picture, classifier that picture, it's going to decide, is it more like, okay, it thinks it's an elephant. Well, you know, that's what happens because we didn't train it anything about lions. We only trained it about tigers. It should be the case. Let's see what happens if we feed it, if we have a picture of a tiger. Okay, let's see how we do on that one. Let's say classifier function, and then let's put in that tiger and see how we do. It says it's a tiger. Good for it. So generally, this will work fairly. You know, what I did will work fairly well for reasonable pictures of these things. I'm sure if we, for example, if we blurred that, let's make that tiger. Let's do this. Let's confuse it by making that tiger. Let's make a blend of that tiger with I don't know, let's paint that tiger blue, for example. Let's blend that with blue. Okay, that's a very blue tiger. Now I have no idea what the classifier will do for that picture. It may do something totally random. Okay, it thinks it's an elephant now. And presumably if we were to make this, if we were to make a table of these, let's say X here, let's make a table of those. And we're making a table here with X goes from, let's say 0 to 1 in steps of 0.1. This will become a bluer and bluer tiger. And now if we say, if we make the corresponding results with our classifier function applied to that, we can see when will the tiger become too blue to be recognized as a tiger. And okay, so it only made it for 2 steps before it gave up and decided it was an elephant. Okay, so let's say somebody's asking about math. Well, let's see, what kind of math would you like to do? Let's do something with some, what's a good example of math? We could do the math I was just studying in the last, this is actually a rather elementary piece of math. Well, here, let's make a random graph. This is always interesting to do. So this is a graph, there are a bunch of nodes, that could be somebody's friend network or something. And we could say for that graph, we could say, let's make a community graph plot, which tries to just figure out which of those sort of, how can we break that into communities of people who are more friendly with each other than they are with other people. But we could, let's try and make another kind of graph. Let's say we make a graph. Well, I can show you my homework here. Let's see. Something I was just working on. Well, one of the things, so one of our goals in in our language is to sort of represent everything in the world computationally. And we've been pretty successful at doing that. There are lots of kinds of things, whether it's geometry or whether it's things with numbers, or whether it's things about human languages, or whether it's things about video and audio and financial data and all sorts of things can be represented computationally. One of the things that I myself have done is I've kind of alternated between doing basic science and developing technology. And so one of the big things that I've worked on is trying to understand fundamental physics in a computational way. And one of the things that's been very spectacular in the last 3 years is a big breakthrough in that area, where we've been able to really understand sort of what physics is made of at the lowest level. And let me just show you a little bit about that, just for what it's worth. So I don't know, we can't, I mean, I'm happy to talk about this for a bit if people are interested, but this is a kind of a big, it's kind of what is the universe actually made of? Well, it turns out the universe is ultimately, everything is made of space, but the actual, what is space? A little bit like a fluid like water is ultimately made of a bunch of discrete molecules. So also it turns out, so far as we can tell, that space is ultimately made of sort of discrete atoms of space, discrete points in space. And the only thing one knows about those points is how they're related to other points, how they're connected to other points. And so you generate this giant graph. So the graph that is our universe right now might have about 10 to the 400 nodes in it. And the whole progress of our universe consists of this graph progressively being rewritten by having little pieces of the graph updated to form other pieces of graph. And so if you keep doing that enough times, so far as we can tell, you get our universe, and you get the features of our universe, like things like gravity and so on, come out as features of this kind of structure. So anyway, there's a whole big story about how, if you kind of look on a small enough scale, that the whole universe ends up being just this giant network. And turns out there's another feature, which is that this giant network, these rewrites that happen, there are many possible different rewrites that can happen. And it turns out that's what leads to quantum mechanics, is the fact that there isn't just one possible path of history in the universe. There's a whole branching and merging collection of paths of history in the universe. And that's what leads to the phenomena that correspond to quantum mechanics. So in an attempt to understand that in a more sort of everyday way, I've been curious about other examples of what I call multi-way systems. So a multi-way system, let's say we have, let's look at something like this. Let's say we say at every step, we're going to replace x by 2x and x plus 1. And we're going to keep doing that, let's say, starting from 1. Let's do that for 4 steps. Okay, and let's label this picture. Okay, so this is showing, so let's see if we can trace this through. This says we start with 1 and it goes to 2. Actually, it goes to 2 in 2 different ways. It can either be just 1 and then 2 either gets doubled to be 4 or gets 1 added to it and gets to be 3. Okay, so the question is, what's this going to do in the end? What's the kind of large scale graph that we get from doing this? So people understand what's happening. 3 can get doubled to 6, or it can get 1 added to 4, and it can actually then get 1 added to 5, and then 1 added again, it comes back to 6. Okay, so let's run this graph a little bit to make something a little bit bigger. Let's say, let's run this 10 steps. Okay, this is what we get. So this has been relayed out. So it's just a graph. So all we know is how numbers are connected to each other. We could lay it out the same way we laid out the other one. We could say, change the graph layout to be, let's see, layered digraph embedding. And then let's tell it aspect ratio 1. And so that's that graph. If we laid it out the same way that we started off laying it out, a sort of more natural way to lay it out is this kind of spider web type thing. I'm sure if we continued this a while longer, would make a bigger spider web, the better to, oops, that's huge. That's a 35,000 node spider web. Let's just try, let's say 14 steps. It's probably already very big. There it is. This is an example of a hyperbolic. If you think about a lettuce leaf, when a lettuce leaf grows, it sort of makes too much lettuce leaf on the edges. And that's why the lettuce leaf has to kind of curl up. And so this thing, if we were to put this as a physical 3D object, it would curl up at the edges because there's sort of too much stuff at the edges. Let's see. So what was I going to show you? I was going to show you my homework today. Where is it? I was looking at, where is it? There we go. This is I write a lot of stuff. You can find, let's see. You can find things that I write. If you're interested in mathematics, this is kind of a rethinking of the foundations of mathematics, kind of changing the way one thinks about the foundations of mathematics from what's been done for the last 100 years or so. It's kind of important. It's something that was kind of a spin-off of our physics project. But anyway, so there's lots of stuff here. Yes, paste the mathematics article, sure. I will tell you that I think the concepts are sufficiently new that in a sense you shouldn't have much difficulty understanding them, but in the end this goes to the foundations of a bunch of mathematical logic and so on. Okay, let's have a quick look at this. Okay, let's have a quick look. Blah 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 blah. Okay, so this is a story of, imagine that you have a mathematical definition that says x dot y is equal to y dot x dot y. So then you can say, so that defines a relation between things. And you could, with that relation, you can start saying a dot b dot a is equal to b dot a dot b dot a. Okay. And so what happens is you'll build up this whole network of expressions. Each node here is an expression made from a's and b's derived by applying this rule here. And so then what happens is a theorem that says that one expression is equal to another becomes a path in this graph. And the proof of that theorem is just giving the steps in the path. So for example, that's the proof of that theorem, is that this thing here is equal to this. This is gotten from one to the other by just applying that rule a bunch of times, and that shows up as a path here. And so anyway, the end result of this whole story goes on for a long time here, but the end result is that we can look at, let's see. Let's see what we have here. Okay, so this basically shows that you probably have not heard of things called semigroups. You probably have not heard of things called groups either. But this is a kind of a piece of abstract algebra. This is a type of mathematical relation. It's a thing that defines a certain class of objects are defined by that relation. And basically what happens is all theorems that are true about those objects end up showing up in this giant network of true theorems. So basically every true theorem will appear somewhere. So for example, I think this is for, that's for group theory again. Somewhere here I probably have logic. Yeah, there we go. This is logic. So this says A and A is the same as A. Or this says that not of A is A. So we can ask, if we use certain axioms for logic, we can say, where do the theorems that we know about in logic show up in this giant kind of ball of this giant graph of all possible theorems, and we start seeing there are different places where theorems that we know about show up in this network of all possible theorems. And so what this is doing is it's kind of showing us that the mathematics that we know about is kind of these little dots in this giant network that represents sort of all possible mathematics. And it turns out the network of all possible mathematics has characteristics that are just like the structure of space in physics. And so there's this huge connection between physics and the foundations of mathematics, or what one can call meta-mathematics, the thing that sort of is the representation of all possible mathematics. And for example, I think I have a thing here where we're looking at, well, that's Euclid. That's Euclid's results about geometry. He has various axioms at the beginning, and from those he proves different theorems. He proves like 400 theorems. That's the network of how the theorems of Euclid are proved from the axioms of Euclid. But we can go on here and look at someplace here. I have, oh yeah, this is, if you really go down to the very lowest level of mathematics, this is the proof of the Pythagorean theorem that uses about 7,000 intermediate theorems that proves from the very lowest levels of logic, proves the Pythagorean theorem. It's a very complicated thing to do. And in fact, if you look at different famous theorems of mathematics, the total number of uses of the axioms are things like 10 to the 36. I think probably I have Pythagoras' theorem here. Do we have this? Oh no, this is, sorry, this is for the Pythagorean theorem. If we fully unroll it, this is the number of times it uses all sorts of axioms of mathematics. So it's ridiculously huge numbers of times. And the way that we do mathematics, it's the same kind of thing. If we were trying to study a glass of water by looking at each individual molecule in the glass of water, it would take us a lot of effort. But in fact, we have kind of higher level ways to study fluid dynamics that don't require us to go down to the level of molecules. And that's essentially what one realizes, is that the fact that we can do higher level mathematics is a consequence of the fact that there is a fluid dynamics-like level of studying mathematics that doesn't go down to this level of individual kind of axiomatic elements. And so that fact, it turns out, the big point of this thing I wrote here is that the fact that higher level mathematics is possible happens for the same reason as the fact that we believe that space is continuous, even though it's really made of atoms of space. And so there are all kinds of fun things you can do with this. But that's, what was I going to show you? I was going to show you my homework, and then we should mention a couple of other things, then we should wrap up here. But let me, where is it? This is my homework. This is what I'm writing this weekend and have to go back to doing. I am studying tic-tac-toe, which you would think was a very trivial kind of thing. Let's just make another version of this and let's make it larger. Okay, and let's, I don't want to mess up my original. Why is this spinning like that? That is a very strange sign. Okay, let's, okay, there we go. All right, let's make this bigger. All right, this was my homework for the, okay, so tic-tac-toe, there's an empty 2x2 tic-tac-toe board, okay? There are 4 different things you can do. Let's say you go another step. There's this kind of tree of possibilities, okay? And if you keep going, you get one of these multi-way systems, just like that one I showed you with numbers. This is one with tic-tac-toe boards instead of numbers. And so what you see is it branches when there are different possibilities, and sometimes 2 things that were, as an example, well, here, for example, this result here can be gotten by going to that state, or it can be gotten by going to a different intermediate state. So the question is, and so now a particular game is a particular path through this so-called multi-way graph. And so you can ask questions like, well, that's the 3-dimensional structure of the multi-way graph. And you can ask questions, okay, that's for a 3x3 tic-tac-toe. That's its full multi-way graph. Let's see if I've got an example here. This is not yet finished or properly developed. This is the game graph for full tic-tac-toe. It's 5,478 nodes, starting from a blank board, and these are all the winning results are down at the bottom here. And somewhere here there are okay. This shows here the purple dots, if you can see them, are where I think the the O player 1 and the orange dots are where the X player 1 in this game graph. So this graph represents all possible. So every possible tic-tac-toe game is a path through this graph. Okay, and so here's a very small piece of this. This is starting from a partially filled in board. This is now showing a piece of that graph, and you can then compute. Okay, this is showing places where there's an inevitable win in this graph, and this is a very poorly drawn graph which doesn't have its arrows in it, that shows the beginning of a tic-tac-toe game, the possible beginnings of the tic-tac-toe game. And so why am I doing this? Well, the reason is that I'm trying to understand more about these multi-way systems that I mentioned are the things that underlie quantum mechanics in particular. And so I'm thinking that by understanding something as familiar as tic-tac-toe, which turns out to have that same kind of underlying structure, that one will be able to understand things about quantum mechanics more clearly. And I need to go back to work in a minute, but let me just, let's see, two things I might mention. One thing I might mention is, for those of you who are high school, in the middle of high school, I recommend, let me pull this up for a second. I'm going to mention two things that are that might be of interest to you. One is our high school summer camp, which unfortunately is full for this year. And actually, as it happens, this is a 2-week camp. And actually, as it happens, we usually do this in the Boston area, although it's a residential camp. And these are, let's see, we can probably look at a gallery of projects people have done at our summer camp. Here, I'll put I can put this the link to this in chat. As I say, this is full for this year, but I encourage people to apply for this, and people end up doing some pretty interesting projects. And I would say that there's a pretty interesting alumni crowd now from our summer camp. Let's see, then another thing I might mention for people who are in the right demographic, we also have a camp, a virtual camp for middle school girls. So if you are 14 or less, let's see if I can pull up the, let me see, summer programs. That's our summer school for grown-ups. That is the middle school summer camp. I believe this is not yet full for this year, and it's coming up very soon. So if people are interested in this and are in the right demographic for it, I encourage you to apply to this, and or encourage your people you know to do so. I can put that in the chat as well. And this is, as I say, this is a 1-week virtual camp. I don't know whether they have. We just started this last year. The summer camp, the main high school summer camp, has been going for a dozen years, and this is a new program. Seemed to work pretty well last year. I will also mention one other thing, which is that for those of you who are actually in the Concord, Lexington area, I have been doing a kind of well, it was originally called Programming Adventures kind of thing, originally with well, it got kind of derailed a bit by the pandemic, but we have been doing a in person in Concord, near Concord Center, kind of weekly session, which was originally with people. Well, originally it was with people who are the age of my youngest child, who is now 17, but then we broke off another cohort of middle school age kids, and I am about to refill the collection of middle school age kids. So if you know anybody who's in the Concord area who's interested in a Sunday afternoon talking about science and technology kind of session, encourage them to, I guess, how to do this, what to do. Well, they can, I guess they could send me email and it will get processed by somebody. I will put my email address in the chat. We, in the past, I also did kind of an in-person thing with high school kids, but as a result of the pandemic and as a result of our summer camp, that kind of segued into a virtual thing with high school kids. And I'm not quite sure how that's, I'm probably going to continue doing that virtual thing, but that has mostly been with people who have come to our summer camp, because those are people who know a lot about our technology and so on. And those become, it becomes an interesting discussion. But if people are interested in that, maybe people who've learned a bunch of about our tech. I should mention, by the way, I should have kind of said this at the beginning, in addition to that hackathon website, another good place to learn about our technology is a little book that I wrote. Where do I have a link to my book? Who knows? That's embarrassing. I don't have a link on my own page to my own book. I'm sure I do somewhere here. Oh, there we go. So this is Introduction to Wolfram Language. Put the link in the chat there. And actually, another thing I can do is I can take this notebook and let me upload this notebook to the cloud. And then I can send you a link to this notebook and you can play with anything that's in here. Okay, let's publish it to that location. It might, we had some big pictures in here, so it might take a little while to upload this. While it's doing that, does anybody have any questions, thoughts, comments? Anything? No? Well, yes, please, Nate.
Yeah, Mr. Wolfram. I was wondering, what would you suggest is the best way to start learning about your language? If
I would
was
look.
interesting.
I would look at the book that I wrote.
All right.
Is the thing I just said. I mean, that's a good place to start. There are many different entry points. I mean, it depends a little bit. If you are already a super sophisticated programmer, there's a little thing called Fast Introduction for Programmers, which is assumes you already know a whole bunch of stuff. The book that I wrote assumes you don't know anything. And it's an attempt to kind of explain from scratch, both sort of computation and our language. Let's see, I have the link here. Let me put this link in chat. And you can, if you would like to pull down the notebook that we used here, that's the link to it. And you should just be able to click on that in any web browser, and it should take you to that notebook. Sometimes it takes a little while for the internal system to cache the notebook. So if you look at it in 5 minutes, it'll work better than if you look at it now. But it should work now. Well, there are very few of you, and I'm not sure if I should offer to do this, but I had sort of said that I would come over to Lexington later this afternoon. I think probably that's a skip it type thing, unless somebody wants to convince me to do that. No, okay. Well, I'm happy to keep working on my homework rather than dropping in with you guys, even though I'd be happy to meet you guys in person. It's always more fun doing these things in person than over Zoom. I have been a remote CEO for 31 years now, so I have been pretty familiar with doing things remotely for a very long time. But I find that these kinds of things are better done in person. Well, any other questions, thoughts, comments? Yes, please. There you.
Yeah. First question. How long have you been like using that like notebook Wolfram thing for?
We invented it in 1987, so 35 years.
Oh. And like second follow-up question to that. Like what I saw today, that like really impressed me. I thought it was incredible, like how much it could do. Since you've used it for so long, does that feeling ever go away for you, or was it like every time it does something, you're still impressed?
Well, we're always making it do more, so I'm always more impressed. No, I really, there are things where you wonder if it's going to work, and it just does, and that's really neat. And the fact is, this computational language that we've made is kind of a superpower for people who learn it. And if you look at people who are sort of in the high end of research and development, lots of different places around the world, there are lots of people who've learned our language and have used it for 25 years and so on. And they're able to do amazing things. And I think, it's sort of interesting to me to see that there are things you have to learn in order to use it well. If you just say, oh, I'm going to do it in the simplest possible way without really understanding what's going on, you will not be able to sort of get that superpower. But once you get it, it's really rather incredible what people manage to do with it. And really the goal is, if you can understand what you want to do in computational terms, then if we did our job, our computational language will let you do those things. But you do have to learn a certain amount about how to make use of that tool. And yes, it's a, what we're doing all the time is building more in the language. And if you look at sort of a plot, there are about 7,000 built-in functions in the language now. And if you look at a plot as a function of time, you'll see that it's been sort of steadily increasing a little bit faster than linearly over the course of the last 35 years. I mean, I originally, to give you a little bit of backstory, when I was probably age of many of you guys, I was interested in physics, and that was the mid-1970s. I had originally been interested in space, but I rapidly segued into being interested in physics. And so I learned a bunch of stuff about physics. And one of the features of doing physics is you have to do all kinds of mathematical calculations. And I was not a big enthusiast of doing those mathematical calculations by hand. I always thought they were sort of boring and mechanical. And I thought, gosh, you should be able to get a computer to do these things. Computers in those days were not as computers are today. I mean, the first computer I used when I was like 12 years old was the size of a very large desk and programmed with paper tape. And it had 8,000 words of memory. So it had about 24 kilobytes of memory. And a very small computer. But so originally my kind of, so I started building systems to do mathematical computation originally for physics. And I built my first big computer system in, 1979 to 1981. And that was kind of a forerunner of what's now Wolfram language. I started building what's now Wolfram language in 1986. I mean, it is sort of funny at some level that the fact that I was not keen to do the equivalent of math homework when I was like 14 years old or something, turned into me building a system that caused millions of other people to, well, not only be able to do their math homework more easily, but also be able to discover lots of interesting things about science and so on. And that's kind of the backstory of what I've done. And now, the good news, in a sense, I've managed to alternate between, I built this thing, this first system I built was called SMP, and I ended up using it to build a bunch of science, and that eventually led to a big book that I wrote 20 years ago now called A New Kind of Science, that introduced a lot of new ideas in basic science that have been rather fertile. And then after that, I went back to doing technology for a while. And actually the ideas in that book are what made Wolfram Alpha possible, and what made things like the natural language understanding system of Wolfram Alpha possible. And then about 3 years ago now, I went back to doing basic science and doing physics. It's kind of funny because I went back to doing the stuff that I was doing when I was like 14 years old and so on. Actually, the very first paper that I wrote, published paper that I wrote when I was 14, 15, I think I wrote it when I was 14, it was published when I was 15, was about substructure of electrons. And it turns out that what I wrote at that time didn't turn out to be correct in actual physics. And I was talking about how electrons might have a size of 10 to the minus 18 meters. And turns out that that's not true. But in our current theory of physics, now 40 something years later, once again, electrons have substructure, and now their possible size is like 10 to the minus 81 meters. So it's kind of like, it's the mistake of 10 to the minus 18 versus 10 to the minus 81 is very, very big difference. But that's so it's kind of a come somewhat full circle. But I think but what my company does is we build, we're constantly building new versions of Wolfram Alpha. Actually, I'll mention another thing. Oh yes, I should mention this. One more thing, one more promotional thing to mention. Let's see, if you go to my homepage, stephenwolfram.com, you will find this section called live streams. And every week I do this science and technology Q&A on Friday afternoons. That's, oh boy, this must have been, is this the one from? No, that was the one from probably last week. And these were questions people asked about what's the densest thing in the universe, et cetera, et cetera, et cetera. And that's a word cloud of different, and you can get this as podcasts and YouTube videos and things like that. And it looks like I've done 92 of these so far. I started doing them at the beginning of the pandemic. I find them fun. They're a good opportunity for me to explain lots of different kinds of things. You can see a variety of different topics here. These seem to be rather physics-oriented topics. I know the most recent one, people were asking about some more engineering kinds of things. The other thing, if you're interested in what we actually do in building our technology, we actually live stream some of the internal meetings that we do. That was one which didn't have much exciting stuff on the screen. So you can, if you want to know how people figure out, what I've been doing for the last 35 years, building this computational language, this is kind of the behind the scenes episode 606. Oh my gosh, I've been doing a lot of these what were we talking about there? We were talking about geometric scenes. So that's talking about geometry and geometric theorem proving and so on. Anyway, okay, any last questions or comments or anything? And if not, I shall disappear. All right, well, if you feel free to, if you're interested in the local Concord area stuff, I guess send me email. If you're interested in the summer camp, apply to the summer camp. If you fit in for next year, if you fit into the middle school summer camp for girls, or know somebody who might, still available this year. And otherwise, nice to meet you all, and bye for now.
Thank you, Mr. Wolfram.
Thank you.
Thank
Thank
you.
you.
Incredibly insightful.
So much.
Bye.
Thank you.